Hello everyone. Today our topic on computer system architecture course is the design of basic computer. In the previous videos we discussed instruction codes, computer registers, computer instructions, timing and control, instruction cycle, memory reference instructions, input, output and interrupt, and the last video was on complete computer description. Functional block diagram of the basic computer is shown in this figure. The basic computer consists of the following hardware components: a memory unit with 4096 locations, each of size 16 bits. The unit has two control signals, read and write, and connected to the CPU through a 16-bit common bus. There are two registers connected to the memory unit: data register to hold the data ready from memory or the data to be written into memory, and the address register, which is connected to the address pins of the memory unit for holding the address to memory location. And since we have 4096 locations, we need 12 bits to address any location. The memory unit can be obtained in a ready form from a commercial source. In the CPU, we have 9 registers: address register, program counter, used to hold the address of next instruction to be executed, data register, accumulator, instruction register, used to store the instruction ready from memory, temporary register, output register, input register, and sequence counter. The size of input register and output register are 8 bits each, so we can input or output one character at a time. The registers and their hardware implementation were presented in chapter 2. In the basic computer, we have 7 flip-flops. I flip-flop used for direct, indirect addressing or to distinguish register reference operations from input-output operations. S flip-flop, which is the bit 15 in the accumulator and used as a sign bit. E flip-flop, and in some computers this flip-flop is called carry flip-flop. R flip-flop for the interrupt cycle. If R is 0, we continue with a usual instruction cycle, and if 1, we start an interrupt cycle. Interrupt enable to enable or disable interrupts, and two control flags, flag in and flag out, used to control the transfer of information from the input device and to the output device. The flip-flops can be of D or JK type. Two decoders, a 3x8 operation decoder and a 4x16 timing decoder. The 3x8 operation decoder is used to decode 3-bit operation code into 8 outputs, D0 through D7, to specify the type of operation. And the timing decoder 4x16 used to generate 16 timing signals, T0 through to 15. The decoders are standard components similar to those presented in chapter 2. The 16-bit common bus can be implemented using a multiplexers or 3-state elements. In addition to these components, we have the control logic gates used to generate control signals required for performing the operation and for controlling the system in general. And today we are going to show how to design the control logic gates. Adder and logic circuit connected to the input of accumulator will be discussed in the next meeting. The control unit of basic computer consists of instruction register of size 16 bits. Bit 15 is transferred to the I flip-flop. The 3 bits for the operation code are applied to an 3x8 decoder to generate 8 outputs D0 through D7, a 4-bit sequence counter with 4 outputs applied to a 4x16 decoder to generate 16 timing signals T0 through T15. These signals, along with other inputs, are applied to control logic gates used to generate the required control outputs to perform a specific operation. The design of control logic gates is the most delicate section in this chapter. The inputs to this circuit come from the 2 decoders, the I flip-flop and 0 through 11 of instruction register. The other inputs to the control logic are accumulator bits 0 through 15 to check if accumulator equals 0 and to detect the sign bit in accumulator 15. For signed values, bit 15 of the accumulator is the sign bit. Data register bits 0 through 15 to check if data register equals 0 or not. The values of the 7 flip-flops. The outputs of the control logic circuits are signals to control the inputs of 9 registers. Most of the registers have 3 inputs: load, increment, clear. Signals to control the read and write inputs of memory. Signals to set, clear, or complement the flip-flops. Signals for S2, S1, and S0 to select a register for the bus. And signals to control the accumulator, adder, and logic circuit. The specifications for the various control signals can be obtained directly from the list of register transfer statements. For clarity purposes, the table for register transfer statements is split into subtables. The first subtable is for the fetch, decode, indirect, and interrupt phases. Here we have the control functions, and here the register transfer microoperations. The second subtable is for memory reference instructions and add, load, store, branch, and conditionally branch and save return address, increment, and skip F0. Third subtable is for register reference instructions: clear accumulator, clear E flip-flop, complement accumulator, complement E flip-flop, circulate right, circulate left, increment, skip on positive accumulator, skip on negative accumulator, skip on 0 accumulator, skip on 0 E flip-flop, and the halt instruction. D7, not I. T3 is common for all register reference instructions, and one of the bits BI is used as an operation code. And the last subtable is for the input, output, and interrupt instruction. Here we have D7, I, T3, common to all these instructions, and one of the bits 6 through 11 from the instruction register is used as an operation code. Here only 6 bits are used since we have only 6 input, output, and interrupt instructions. Here again the common bus structure along with the memory and registers. For example, to transfer the contents of program counter into the address register, we need to apply 010 on the select signals to select the program counter, so its contents are transferred to the bus, and to apply 1 to the load input of the address register, allowing the contents of the bus to be transferred to the address register. Suppose that we want to derive the gate structure associated with the control inputs of AR. We scan the tables to find all the statements that change the contents of AR. Back to the tables. On the first subtable, we have the microoperation, not R, T0, program counter to address register, and here we have the address register, instruction register 0 to 11 to address register. On not R, T2. Here we have as well memory address, memory location addressed by the address register to the address register. On not D7, I, T3. Here we have as well clear AR on R, T0. And by scanning memory reference instruction table, we have here AR, which is for the branch and save retain address. Increment AR. AR plus 1 is stored in AR address register, and this is on D5, T4. Here we haven't any other operations, and in register branch instructions we haven't any operations, and on input output also we haven't. These are the statements that change the contents of AR. The first 3 statements specify transfer from a register or memory to AR. To perform that, the contents of the register or memory is placed into the bus, and the contents of the bus is transferred to AR by enabling its load control input. So if we have some register, this is the bus or memory, address register. So after placing the contents of the selected register or memory into the bus and activating the load input of the address register, the contents of the bus are transferred to the address register. The next instruction clears accumulator to 0. In this case, we have to apply control signal to the clear input of the address register. And the last statement increments AR by 1. In this case, we have to apply a control signal to the increment input of AR. For this purpose, we have to apply 1 or a control signal to the increment input of the address register. The control functions can be combined into 3 Boolean expressions as follows. here the load input of the address register equals to not R T0 or not R T2 or not D7 I T3. Next, the clear input of the address register equals to R T0. And the increment input of the address register equals to D5 T4. Now, having these expressions, we can draw the logic circuits for generating the control signals associated with the control inputs of AR. This is the address register. The size of the address register is 12 bits, and the size of the bus is 16 bits. The least significant 12 bits from the bus are loaded into AR, and if AR is source, the contents of AR are loaded into the least significant 12 bits of the bus. For example, for increment, we have D5, T4. When this value is 1, the contents of the address register are incremented by 1. The load input equals to 1 if this expression is true, or when one of these inputs equals to 1. In the same manner, we can design the control gates associated with other registers. The logic gates associated with the read input of memory is again derived by scanning the tables to find the statements that specify a read operation. And we are scanning the tables for this symbol. By scanning the tables, we have the read on these cases, not RT1, not D7 IT3, and T4 ANDed with D0 or D1 or D2 or D6. And this expression are in this case read should be applied to the read input in memory to perform the read operation. And for performing the read operation, the select lines S0, S1, S2 should also be applied to the bus, and in case of memory, they are 1, 1, 1. So having 1, 1, 1 and the control signal read, the contents of memory location addressed by the address register are read and transferred to the data register. Next, control of single flip-flops. The control gates for the 7 flip-flops can be determined in a similar manner. For example, table shows that interrupt enable may change as a result of the two instructions, interrupt on and interrupt off. And the control function for setting the interrupt flag is D7 I T3, and it would be 7. And for clearing the interrupt enable D7 I T3, and it would be 6. Moreover, an interrupt enable is cleared at the end of the interrupt cycle on RT2. If you use AJK flip-flop for interrupt enable, the control gate logic will be as follows. This is D7 IT3, and it would be 7 is applied to the J input, and with B6 is applied to the K input. But we want to reset it also if RT2 is true. And the output of this JK flip-flop is applied to the interrupt enable flag. Next, regarding the control of common bus, the 16-bit common bus is controlled by the selection lines S2, S1, S0. The decimal number shown with each bus input specifies the equivalent binary number that must be applied to the selection inputs in order to select the corresponding register. For example, to select memory, here we have 111, to select data register 011, to select accumulator 100, etc. The following table specifies the binary numbers for S2, S1, S0 that select each register. Address register is selected on 001, program counter 010, data register 011, etc., and memory on 111. Each binary number is associated with a Boolean variable x1 through x7, corresponding to the gate structure that must be active in order to select the register or memory for the bus. For example, when x1 equals 1 here, the value S2, S1 is 0, should be 001, and the output of address register will be selected for the bus. And for example, on D61, the value of S2, S1 is 0, should be 110, and the output of temporal register will be selected for the bus. This table can be used as a truth table for an encoder for bus selection circuit. From the table S0 equals to X1 or X3 or X5 or X7, and S1 equals X2 or X3 or X6 or X7, and S2 equals X4 or X5 or X6 or X7. The three encoder outputs are applied to the multiplexer bus select inputs. For example, when X1 equals 1 here, the output of the decoder is 0, 0, 1, and therefore the output of the address register will be selected for the bus. Here 0, 0, 1. So the output of the address register will be selected for the bus. To determine the logic of each encoder input, it is necessary to find the control functions that place the corresponding register onto the bus. For example, to find the logic that makes X1 equals 1, we scan all register transfer statements in the table and extract those statements that have AR as source. And these statements are AR to program counter on D4, T5, and AR program counter on D5, T5. Therefore, the Boolean function for X1 is D4, T4 or D5, T5. The data output from memory are selected for the bus when X7 equals 1 and S2, S1 is 0 equals 111. The gate logic that generates X7 must be also applied to the read input of memory. Therefore, the Boolean function for X7 is the same as the one derived previously for the read operation. In a similar manner, we can determine the gate logic for the other registers. Our next topic is design of accumulator logic, and this will be the last section in chapter 5. For today, that's all. Thank you.